Hello and welcome to this video today. We have recently introduced the determinant, and in this video we're going to collect a few useful properties of the determinant. These will later help us in devising methods for actually computing the determinant. So this video is dedicated to properties of the determinant. And as I said, the goal here is to collect some properties that will help with computations. Let's first have a look at how determinants behave under row operations. You will of course remember that we introduced row operations in the context of systems of linear equations. The idea was to introduce operations on the tableau, or on the matrix, that do not change the solution set. If the solution set is not affected, then of course other important characteristics of a matrix will also not be affected. For example, these operations will not change the rank of the matrix. And we introduced the determinant with the idea that it should somehow be connected to the rank. We'll make this more precise in just a few minutes. But that makes it a natural question to ask, what is the changes to the determinant induced by these elementary row operations? And that's what our first theorem will be about. So this is on the behavior of determinants under elementary operations. So let's say we have a matrix A that we start with. So that's an n by n matrix. And let A bar also be an n by n matrix that is obtained from A through some elementary operation. In the following, we list these operations and then look at the results, at the changes of the determinant. So then the following holds. First, let's say A bar is obtained from A through the addition of a multiple of one row to some other row. So this is basically the most important elementary operation that we use in Gaussian elimination processes. And the result of the theorem is that this operation does not change the determinant at all. So we are free to add multiples of one row to some other without doing anything to the determinant. So if A bar is obtained from A through addition of a multiple of a row to some other row, then the determinant of A bar is the same as the determinant of A. So that's the easiest elementary operation in terms of determinants that we have, and that's also one that we'll use most frequently. Second, a little more complicated, if we just want to multiply a row by some constant, some lambda, without subtracting or adding it to some other row, then the value of the determinant will change, and it will change by precisely that constant. So the statement here is, if a bar is obtained from A through multiplication of a row by some lambda in R, then the determinant of the new matrix A bar is lambda times the determinant of the old matrix. So the determinant is also multiplied by lambda. And finally, one more important operation that we frequently use is exchanging two rows in the matrix. So we need to take care of that as well. So let's say a bar is obtained from A through the exchange of any two rows, and we just exchanged two rows here. Then the determinant also changes, but the change is very subtle, so to say. What does change is the sign. So the new determinant is minus the old determinant. So whenever you exchange any two rows, you also have to flip the sign of the determinant. Now, in particular, if A contains a zero row, then according to this second property here, this one, we can of course multiply this zero row by zero without actually changing anything. So that means if lambda equals 0, and we choose to multiply a zero row by 0, then of course this formula also holds. So the new matrix looks like the old one. But according to this formula, the determinant of the new matrix is then 0 times the determinant of the old one. And that of course implies that the determinant is already 0. So whenever a matrix contains a 0 row, then its determinant will be 0. And that is actually an important consequence. So just take a quick note of that. In particular, if A contains a 0 row, then the determinant of A must be 0. Now, looking at this theorem, basically that tells us that we can manipulate rows in a certain way. There's one statement that is a little more general that we will not use very often, but it's good to know it still. And that's why I'm going to list that as a theorem of its own. That is called the so-called multi-linearity property of the determinant. And that is a more general version of at least the first two properties that we listed. The idea here is the following. Let me write that down formally. So let's say we have vectors R1 to Rn that are in R to the n. We have an index j that is between 1 and n. And we have a vector rj hat that is in Rn as well. And also two scalars, let's call those lambda and mu in R. Then we look at the determinant of a certain matrix, namely the matrix spanned by those R's. So let's say we treat those as row vectors of a matrix that contains R1 transposed as its first row, then R2 transposed as the second, and so on. At some point we have Rj-1 transposed. And then let's say the jth row. That looks a little different. That is composed of two vectors, or more precisely, the jth row is a linear combination of two vectors. More precisely, it's lambda times Rj transposed plus mu times Rj hat transposed. And then again, all the other rows are just the Rj plus 1, to Rn. So that's a matrix made up of n rows, and the jth row is a linear combination of two vectors. And we want to know the determinant of that one. Then we can relate that to the determinant where this linear combination is separated. More precisely, what we get is, let's have a look at first at the matrix. That looks just like this one, but it only has the Rj part in the jth row. So what changed here is the Rj part and here's the Rj part. So that's a matrix that only has that first part in. And let's also consider a matrix that only has that second part of the linear combination. So again, copy all the rows. Then we'll only take the Rj hat. And then we'll copy all the other rows. So again, that's also a matrix. And that contains this Rj hat part here, this one. And what this theorem now says is, well, the determinant of that first matrix is equal to basically the same linear combination of the determinants of those two matrices. So we compute the determinants of those two. And we take the corresponding linear combination. Right, so basically we can expand that linear combination of one row into two matrices by just copying all the other rows. And then the determinant of that original matrix is equal to the sum, the weighted sum of those determinants of the new matrices. Looks a little complicated. As I said, we won't need it very often, but basically that's just a generalization of the other two properties. Also note, I'm not writing that down formally, but the same property can be applied to column vectors. So if a column is a linear combination of two other vectors, then you can do the same for the columns. So just as a side remark here, the same property applies to column vectors. So why are these properties useful? Basically, if we can apply elementary row operations to a determinant with the matrix that we want to compute the determinant of, that means we can bring that matrix into echelon form. Now, if we have a system of linear equations, we know that can be brought into echelon form. And we also know that if that echelon form happens to have a zero row somewhere, then the determinant will be zero. So basically that means if we have a matrix that does not have full rank, then its echelon form will necessarily have a 0 row, and then the determinant will be 0. On the other hand, if a matrix has full rank, then its echelon form will not have a 0 row, and that means this matrix will not be 0. So that is basically the one theorem that captures this characterization of rank and determinant. And that's what we were going for. So this is basically the central theorem for us of determinant theorem. So connection between determinants and, let's say, invertibility. And again, let me formulate that. So if we have a matrix, an n by n matrix, then our theorem says then A is invertible if and only if it has full rank. And that is the case if and only if the determinant of A is not 0. And in particular, if we have a system of linear equations of the form ax equals b, what can we say about the solutions? So the SLE ax equals b that has a solution for every possible right-hand side B if and only if the determinant of A is not 0. So basically what we do is we get that solution. If the determinant is not 0, we know that we can invert the matrix A. So by multiplying with a to the minus 1 from the left, what we get is this here. And that means x equals a to the minus 1b. So that will have a unique solution for every possible right-hand side b. Okay, so that's the main result of this section here. Let me just add one more theorem at the very end of today's video that summarizes a few other interesting results about the determinant. Let's say we have two matrices, A, B in R to the n by n. Then the following hold. First, a very simple result about the transpose of a matrix. So if we take the determinant of the transpose of a matrix, then this does not change the determinant. That means determinant of A transpose is the same as the determinant of A. And that justifies why we've only talked about rows so far and ignored columns. Basically, the results are the same for columns. So if we want to work on columns, we can just transpose the matrix without changing anything about the determinant, then work on the rows and then transpose back again without changing anything. So everything I've said about rows so far can also be formulated in terms of columns. Second property, this is where B comes into play. The determinant of a product of two matrices, that's interesting actually, is the same as the product of the determinants, like this here. In particular, for some k in n, the determinant of a to the power of k is equal to the determinant of a to the power of k, like this. So if we know the determinant of those two matrices, A and B, then we can compute the determinant of AB right away without actually knowing what AB is. And finally, again, a special case of that. If the determinant of a matrix A is not 0, then we can also know the determinant of A to the minus 1, and that is 1 over the determinant of A. Why is that the case? That's easy to see as a special case of that second property here, because as you know, A to the minus 1 times A is the identity matrix. So that means the determinant of A to the minus 1 times A is the determinant of the identity matrix, of course, and that determinant is 1. You can just do the computations. That's easy to see. So applying that determinant multiplication theorem, that second property here, this expression is the same as determinant of A to the minus 1 times determinant of A, that is 1. And then of course we can just solve this for the determinant of A to the minus 1, which is then 1 over the determinant of A. Okay, so that's just a little remark at the end, how to use the second property to prove the third one. So that sums up many important properties about the determinant. And in the next videos, we'll then use these properties to come up with methods to actually compute the determinant. And of course, I'll see you then.